Okay, I want to welcome all of you. There are still seats scattered around, in particular down in the front. There are some in the very back as well. But we'll give people a minute or so to get seated. My name's Tim Swindle. I'm the director of the Lunar and Planetary Lab, and I want to welcome all of you here today. We're celebrating the Parker Solar Probe and our studies of the sun as well. And I'm very happy to introduce our lecturer, who is Professor Joe Giacalone, who is on the faculty here. He got his bachelor's at Fort Lewis College in Colorado and his PhD at the University of Kansas, and has been on the faculty here for 20 years, something like that, give or take?
I've been on the faculty for 15 years, something like that. But I've been here for 25 years. Yeah.
And he's been a leader both nationally and locally, and is a co-investigator on Parker Solar Probe. And so without further ado, I will turn it over to Joe Giacalone.
Right. Thank you. Thank you very much. Are we okay, Bert? Okay. Okay, wow, I am really excited about this crowd. This is quite a turnout for mid-July in Tucson, in the middle of the day, you know. Thankfully, it's cloudy outside. We're in the middle of monsoon season. I guess that's the trick, to do it during the monsoon season. As Tim says, I'm Joe Giacalone. It's a nice Irish name, as they say. That's right. I am a co-investigator for one of the instruments on Solar Probe. I would like to start with a dedication to my dad, who I don't want to make this a really sad note, but my dad passed away this week. And this is a picture from 50 years ago. 50 years ago, my dad and I, he was about 26 at that time, and I was about 6, underneath our eucalyptus tree in San Diego. Dad was an absolute enthusiastic reader, writer. He always wanted to be a writer, an author. He had the most creative mind, very strange, odd, crazy, fantasy-like short stories that he would write, and he just loved science fiction. And so when I kind of went into science, he was very excited about that, very proud of me. And through the years, we had lots of conversations, and it got to be kind of a running joke, because every time I'd go see him, he would ask me, "So what is it that you do?" And I would explain it to him very, very carefully as I could. I've lectured many times, so I think I know how to explain things reasonably well. He'd sit there with a nice smile and ask some questions, but then, I don't know, a year later I'd visit him again, and he'd say, "So what is it that you do?" And it just, through the years, it was like that. So Dad, I hope you're listening. This is for you. Okay. Okay, so why do we study the sun? Okay, I always like to start with a question like this. Why is it important? Well, first of all, the sun is a star. Okay, it's a star that's very close to us and accessible to us to study in close detail. So this is a good opportunity to study a star in detail. I got to find a laser pointer here. I'm not going to be able to function without it. Okay, actually, I don't know. Well, I guess I'll have to figure out how to function without it. Okay, the other thing I'd like to say about the sun is literally the dominant source of energy in our solar system. I always like to start with a little fact. Thank you. Boy, all I had to do is say, I can't operate this laser pointer, and wow, people. Thank you, Tim. Okay. I like to start with a little simple fact. Actually, if you take all of the energy consumed in the United States the last year, you could look it up on Wikipedia. You can look up how much energy was consumed. Most of it traces back to the sun anyways. Fossil fuels and hydroelectric, all this stuff traces back to the sun. If you take all of that energy consumed last year and you work out the energy consumed and multiply that by 1,000,000, how much energy we use in 1,000,000 years, you would equal the output of the sun, the energy output of the sun, in 1 second. Okay? So the sun is the dominant source of energy in the solar system, mass and other things. Most energy, basically all forms of energy except for atomic energy, can be traced back to the sun and is responsible for life. It is absolutely worth our study. And we also know that the sun changes. Okay, it's not this constant thing that we see in the sky, not just the rising and setting, but just the sun itself changes. And these impact Earth. This space weather does significantly affect Earth in ways that we do not fully understand. There's the sun that we see and have seen since the dawn of human civilization. This is another one of my favorite pictures. This is Chaco Canyon, Fajada Canyon in northern New Mexico. Has anybody been there to this? Wow, lots of people. Okay. This is essentially a calendar. It's a petroglyph. It's a calendar. It's situated between, so that the sunlight shines on it in such a way that they know the time of year. And so this is the study, where the sun is in the sky, the constant sun, not the changing sun, but just it changes because of the way we view it, has been known through the years. It affects Earth in a lot of ways. The constant sun, first of all, my guess, since we're doing this in the summer and we're not doing this in February or March, most people here probably live in Tucson. We don't have a lot of snowbirds here, or students. But for those who are from Tucson, probably know what I'm talking about. Those who aren't from Tucson, we do have seasons, okay? The saguaro cactus blooms May. I guess I'm getting a little feedback, so I'm going to lower it. Oh, okay, thank you. Okay, good. Right. I'm not trying to get away from everybody. Okay, they bloom in May, June timeframe. This is the Arizona poppy in the lower right? It's I typically see them July, the monsoon season. You typically see them come out. They come out in the spring too, but they're most common where I hike on the Yetman Trail after big monsoonal rains in the summer. And yes, it does snow in Tucson. That's my house. I have proof, and I do live in Tucson. And there's also long-term. So there's also they got the day-night cycle. You have weather. Weather is all related to solar energy. The seasons. There's also long-term changes that lead to ice ages and warming trends on the planet, having to do with Earth's orbit. Earth's orbit around the sun changes. Our orbit is pretty close to circular, very small deviation from being circular, but that's not always the case. On scales of many thousands of years, the orbital eccentricity changes. Its tilt on its axis also changes, on scales of long periods of time. There are periods where they all conspire in such a way that an ice age would be the most likely, very probable outcome. So these are referred to as Milankovitch cycles. Okay. But we only see part of the sun. And by the way, I love pictures like this. And I have at the end of my talk, I have a few more. This is actually a soldier. This is I think it was the Kuwait, way back in, early 90s, I think it was. But it's a soldier, so holding the sun. There's the sun that we see. Actually, you're not supposed to look at the sun, but please don't ever just look at the sun. Even during a sunset, don't stare at the sun. If everybody sort of peripherally glances at it, you kind of know we all know what it looks like. What you're seeing there is the photosphere. That's a very thin layer of the sun. So you're really only seeing hardly anything. Okay, we can't see inside of it. Well, you can, but you have to know what you're looking for. And outside, in particular, is what I want to talk about. We know that the atmosphere actually changes, and its changes are very real. Okay, and the changes are unpredictable. They're mostly unpredictable. So here's an example. This is a movie. I believe it's a Soho made to look like an eclipse. When the moon passes in front of the sun in the sky, you get an eclipse. Okay, and then what you're seeing is no longer the solar disk if it's a total eclipse, not an annular one. If it's a total eclipse, you see the corona, the solar corona. It's the outer atmosphere of the sun, and it's very dynamic, changing on a wide variety of scales, days, hours, changes on all sorts of scales. This is the earliest known petroglyph thought to depict a corona, and presumably these little bubbles are little bubbles coming off of the sun. This is from Ireland in 3340 BC or BCE, before Common Era, from Ireland. The date was even on here. Presumably the date is on there. I had to think about this, by the way. The date is on there, I believe, because we know the eclipses. Okay, you could date the petroglyph, but then we know exactly the dates of eclipses because those are based on orbital dynamics, and that can be done very carefully. So anyway, so the corona is constantly dynamic. It's changing. So the sun changes. It's clearly changes. Okay, then we had a big eclipse last August. Anybody in totality last year? Oh, like mostly everybody. Wow. You notice my hand was down. I was here. We had a great event. And I'm going to say this. We had more people on the mall out here for the partial eclipse here in Tucson than we get for tailgate parties for the U of A football team. So that's right. It was packed out here. It was so great. And that was also in August. It was hot. I don't know if you remember last year's monsoon season. Most of our rains were from like mid-July to like the first or second week of August. We had nothing for several weeks, so it was like a hot period in late August. Okay, so this is a comet, just to show that effects happen. Okay, this is the comet. Look at its tail constantly being disrupted. It's on repeat. This is an image of the solar corona produced by a white light imager. We're going to have a similar one of these instruments on Solar Probe. And it's looking not at the sun, it's looking off to the side. So you're seeing the atmosphere, the corona, as it's changing. And you can just see the effects on the comet. And this is a large object. A comet's a large object. It's not a planet, but it's pretty big, and you can clearly see these effects. This is another image of the sun that you can't see from the ground. You have to go into space to see. This is an X-ray image. It's actually extreme ultraviolet, but there's some overlap in the spectrum. I just like to say there's X-rays. This is the sun with X-ray vision. Okay, forgetting about this for a second, the X-rays here are it's an emission spectrum, but you need extremely high temperatures. The solar corona is well over 1,000,000 degrees Celsius. So it is extremely hot, and that's why it glows in X-rays. And you can see it's variable. It's variable on days. And this is the part of the sun that is quite interesting to us. This solar flare. So this is a solar flare. Solar flare is a big, bright flash in X-rays, and they have different classifications. This was what's called an X-class flare. It has to do with how much X-rays come off. Okay? It was so bright that actually the X-rays spilled onto neighboring pixels. That's why it's got that funny look to it. It was actually just a very small point. Okay? We can work out the energy released in that flare, not just in the X-rays, but other forms. We know where the energy came from. The energy came from very strong magnetic fields in the sun. And you can work out how much energy was contained in that magnetic field over the volume of that size. Okay, we can work out the total energy. Just another interesting fact about the sun. That energy is 100 times greater than the kinetic energy of the asteroid that smashed into the Earth about 170 million years ago, leading to the extinction of the dinosaurs, creating Chicxulub crater down in the Yucatan. Okay, that was an event that led to the extinction of the species. It's an extinction level event, 10-kilometer size asteroid. That is huge, moving at 25 kilometers per second when it smashes into the Earth. And the kinetic energy of that, which is enormous, is 100 times less than that. Okay. So again, the sun is worthy of studying. Okay, this is basically a spacecraft artificial eclipse, although that's an X-ray image in the center, but this is a occulting disk, so it's basically like going into space and putting your thumb up in front of the sun. I've got it on repeat because I want to talk about some of these things. Anyways, but you're looking at the corona, basically. Elapsed time over several days around the Halloween period of 2003. These are called the Halloween storm period. I believe this is Mercury. If somebody knows it's something else, they can correct me, but I think it's Mercury. It could potentially be Venus. These are the stars moving in the sky. So you can kind of see the sun moves relative to the stars and the planet moves relative to the stars. It's great for an Astronomy 101 talk about Kepler's laws and retrograde motion and all this sort of stuff. But the dynamic, okay, so this snow, you see how dynamic it is, and then you get this huge snow striking the detector. So first of all, the dynamics we're trying to understand of the sun, but secondly, this snow that gets created, these are basically high energy charged particles that get accelerated by the sun. They're particulate radiation. They're mostly protons and electrons, but some heavier particles as well. And they basically hit the detector and cause problems. Okay? They're not direct images, they're actual, it's like you're taking your camera and it's turning into a particle detector. That's my research focus is mostly on that aspect. The changing sun does affect the Earth. We absolutely know that it does, but it wasn't known it wasn't really known until the 1800s. The effects are subtle on your day-to-day lives that don't have anything to do with technology. Okay, so if you're not, in the pre-cell phone era, actually you'd have to go back to the pre-telegraph wire era. Okay, then sun's effects were not very well understood, although you'd have the aurora borealis you would see. But nobody made the connection between changes on the sun, which required sophisticated telescopic observations anyways, because you don't see that activity, these solar storms, when you look at the sun in what's called white light. You don't see these storms. You can, by the way, but you need kind of a sophisticated telescope for that. So making the connection between changes on the sun and changes on the Earth was not really done until the 1800s, when we had good, better telescopes, certainly better telescopes than we did in the Galileo era. And it was Carrington, and there was a huge event, perhaps regarded as the biggest event that has occurred, bigger than anything we've had so far, was this Carrington event. But we didn't have spacecraft back then, so we weren't observing the sun back then. Certainly technology notices, by one estimate, you could just go to Wikipedia, by one estimate during a solar maximum, I'll tell you what that is in a second, the collateral damage to technological kinds of things is $1 trillion per year. So industry notice, technology notices. It might not affect your individual, maybe your cell phone, you cut out on somebody and you're like, you get a little frustrated, but it comes back in a little bit. Hopefully it's not a Y2K kind of level thing, of course Y2K never happened, but do you remember all of the hype about it, that we were worried that our bank accounts would be zeroed out and all of that sort of stuff? We just hope something like that doesn't happen. This in the lower right, not this, but this here is an estimate of ground level currents, and so when a solar storm hits the Earth like this, the Earth's magnetic field shakes around, and that produces currents in the ground, and that can overload power grids. And this is kind of an estimate of where potential blackouts could occur. Sperm whales are thought to navigate by magnetic fields, maybe. But one thing that is true, in the 1800s, when unfortunately we were slaughtering a lot of these animals, we had lots of observed whale strandings. Okay? And we counted up these strandings. Somebody kept statistics of that and found out that the whale strandings, the number of strandings, were highest when the number of sunspots was the highest, what's called sunspot maximum. So they correlate with the solar cycle. Yeah.
Where's Tucson on the map?
Yeah, good point. Tucson is down here somewhere. Right? Yeah, right there. That's probably Phoenix. So yeah, that's probably us right there. Yeah. 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 We're safe, right? That's right. Homing pigeons, I've heard stories about homing pigeons being confused. They're probably just stories. Maybe, but I don't know, maybe. And then there's there's a scientific study being done on what's called the snowshoe hare. It's a rabbit from, Canada, region, Alaska, Canada. They apparently their population correlates also with the sunspot cycle, and it's thought to have something to do with maybe the soil changes or something like that. But anyways, it's interesting. You should probably check out. It'd be worth checking out you're going to NOAA's website. NOAA actually does keep track of space weather and their effects. Just to point out that it is important because today's world, not just do we personally rely on technology, but there's a lot of interdependencies, the electric power, transportation, emergency services, government services, oil and gas, water, banking are all interconnected. So if we disrupt one of these chains, it could potentially be a very significant effect. And I know that governments, the US government and I know other governments take this very seriously. And so it is important to understand this. More directly, there was an interesting, this is one of my favorite plots, is that increased solar activity, when the sun gets very active, the Earth's atmosphere expands a little bit, heats up just a little bit, but it expands. And that is actually a major problem for orbiting spacecraft, because orbital decay is a very significant effect. Okay, it's thought that when solar maximum occurs, that actually sweeps out a lot of that space junk that we have orbiting the Earth. This is one of my favorite plots. This is a SAMPEX, which is a spacecraft that was in orbit around the Earth, launched in 1992. Down here is the sunspot cycle. Here it's high solar activity, low solar activity, high, low, so on. And you'll notice we launched in 92. It had a kind of a slow change, but mostly constant. But then during that next solar maximum, it really decayed that orbit. And then the next solar maximum wiped it out totally. It was basically November of 92 when it entered Earth's atmosphere. So this happens commonly. This is a very well-known thing. So if you're in that industry and you're going to launch a spacecraft, it would be good to know about this, because you might want to put some thrusters on there to avoid things like this. Whoops. Oh, now I'm changing slides. Okay. Well, I can do that. This is and then it has a more pleasing effect. This is my backyard. This happened in Tucson. So you can get an aurora, and I always like to say this is not a sunset because that's not the sun. That's the moon that I overexposed. I took this picture back in the days of film. I didn't know what exposure to use, and this was the lowest exposure I had. All the other ones were way overexposed. But you can see the stars, and this was the aurora to the north. So I'm looking towards the west. The sun was setting. 2001. So, and this is where we are in the current solar cycle. If you're interested in knowing, we are in the declining phase. Okay, starting to approach the next solar minimum. Solar maximum is the period. This is basically sunspot number. It's not directly the number of sunspots because not all sunspots get counted the same. Bigger sunspots get a higher weight than smaller sunspots and so on. But they have a method of counting them, and this is essentially the number of sunspots versus time, and it has this very well-known 11-year pattern. This has been known since the 1700s. This very well-established 11-year pattern, and it doesn't go out of phase. It's very nicely phased at 11 years. There was a period of time, incidentally coinciding with the lifespan of Isaac Newton, where there were very few sunspots during that period. It's called the Maunder minimum. And so it wasn't discovered actually until after that, the mid-1700s. Galileo observed sunspots, and he was counting them, but they didn't see that 11-year cycle so clearly because that Maunder minimum period. And then afterwards, I think it was Hale that first noted this 11-year sunspot cycle. So right now, we're in solar minimum. Okay, and then the sun's influence reaches a long ways. The so-called sphere of the sun's influence extends all the way out, at some point encounters interstellar space. So the sun's atmosphere is continually expanding. That's what's known as the solar wind. The solar wind continues to go out until it peters out. It's the number of particles, because it's a sphere and everything's moving out radially, the number of particles falls off with distance. Okay, so the speed roughly stays the same, but the power of it goes down because it's a 1 over r squared. It's kind of like standing farther and farther away from a light bulb. The light bulb dims the farther you get away. Same sort of effect. And at some point, the interstellar gas is stronger. And when that happens, it dominates. But that distance is about 100 to 150 AU, something like that. There are a couple of boundaries that get created well beyond the orbits of the planet. And Voyagers 1 and 2, which are still active, producing data. I'm not a co-investigator, but I'm a member of their, what's called a guest investigator for Voyagers 1 and 2. And these two spacecraft still active, still producing data. They're true exploratory missions. Voyager 1 has just crossed the heliopause recently and is now in interstellar space. Not pristine interstellar space because there's still effects from the sun that can be felt out here, but it's not measuring gas that came from the sun. The gas there is from the interstellar origin. Voyager 2 is trailing right behind it, has not yet crossed that boundary. This bubble is known as the heliosphere. And there's a little display out there. You can turn the knobs. You can make a little heliosphere with water flowing through a little pipe. I don't know, did anybody look at that out there? The little heliosphere display. You can change the solar wind speed, which is the thing shooting out. You can change the interstellar gas speed and see how it affects the bubble. To me, I think it's the best simulation of the heliosphere. There's lots of numerical simulations too, but I love that one because you can do it in real time. Okay, so I'm going to just list a few of the many mysteries of the sun, and then I'm going to start talking about Solar Probe. Not all of these questions are going to be addressed by Solar Probe. Okay, this one is one of the primary reasons why we're sending a mission to the sun. We want to understand what heats the solar corona. The solar corona is like 1,000,000 degrees. It's almost as hot as the center of the sun. The outer atmosphere, think about that. The outer atmosphere of the sun is about as hot in terms of kinetic temperature as the interior of the sun. There's Obviously, the center of the sun is much more compressed, has a lot more matter, and the outer atmosphere is very tenuous, but in terms of the kinetic temperature, it is 1,000,000 degrees, the outer atmosphere, okay? We don't understand that. The photosphere, what you do see, that's only at about 5,000 or 6,000 degrees Kelvin, okay? And it goes from 5,000 degrees in the photosphere to 1,000,000 degrees over a very short distance. Several hundred kilometers, well, several thousand kilometers, but it's something of the order of the thickness of an onion skin on an onion, okay? Amazingly short distance that you go from that really hot temperature. We don't understand that very well. It's actually, it's dependent upon location, okay? But it is really amazing. We don't understand that. We don't understand what heats the solar corona. Where does the solar wind come from? Obviously, it's extremely hot, and so the gravity of the sun can't keep it in, and so it goes out, and that's what forms the solar wind. But we believe it comes from very specific places on the sun, and we don't understand that extremely well. What causes flares and coronal mass ejections? We may be able to gain some insight into that very important question. What causes the sunspot cycle? Why 11 years? Okay, we don't understand. We have little models for that, but we don't understand it very well. This mission is probably not going to answer that question, but it is a very important question. How does the sun interact with the interstellar medium? An important question as well. And then how does it influence cosmic rays, which I haven't even talked about. These are all some big questions about the sun. Okay, solar probe. Along comes solar probe. Well, solar probe actually has been a concept since 1958. We didn't just come up with this idea. It was actually predates NASA. John Simpson, University of Chicago, James Van Allen, University of Iowa, were on this space science board, which predates NASA, and they wrote a report about things that we could be doing relating to space physics, and one of them was to send a probe to the sun. Okay, so that was an initial concept. Early concepts involved, it's actually very hard to get to the sun. it's because the orbital speeds get extremely high the closer you get to the sun. That's just the way Kepler's laws work. And so it takes a lot of energy to make changes and things like that. So it's actually quite difficult to get really close to the sun. Some of the early ideas with the propulsion systems in the 60s was to use a gravity-assisted Jupiter. Think about that. You got to go 5 AU out to get really close to the sun. It's kind of an interesting idea. Then just the way the machinery of other interests come up. People want to do this, they want to do that. It's very costly to do this. There were various other discussions. I could probably have 3 or 4 other slides in here, but I don't want to go through that. But in 2002, our field, what's called heliophysics or space physics, had a decadal survey, which sort of maps out the next priorities for the next 10 years. And solar probe in that decadal survey was the #1 priority, that we really need to focus our resources on doing this. It was later reaffirmed in the 2012 decadal survey. It was approved as a Living with a Star. That's a program at NASA operated by the Goddard Space Flight Center. Proposals 2009, 2010, thereabouts. Phase A began in 2010. Phase A is the first part of the study in 2010. And then the launch date was 2018. I went back to some of my old slides because I was an investigator in 2010. I was on one of those proposals. And the launch date was July 31st, 2018. Okay? It has been changed by 4 days. But that's still pretty phenomenal to pick a launch date and to stick with it all the way through. We've changed it by 4 days. Okay, we've changed it by 4 days. Okay. I always just like to show this. This is okay, so Friendship 7, part of the Mercury program. Friendship 7 was the spacecraft that John Glenn was in, the first American to orbit the Earth. He orbited it for 3 days, and he was in Friendship 7. That's what Friendship 7 looks like. There's a heat shield here, so when it's coming into Earth's atmosphere, the heat shield keeps John safe. Okay, this is Solar Probe. It's about the same size, and Solar Probe, for obvious reasons, has a heat shield. Okay, it's going to the sun. You got to have a heat shield. Okay, so it has this big heat shield here. But what's interesting is they're not that different. They're about the same size. They're about the same size. The drawings are to scale. So, and I think I believe it's in the Air and Space Museum. Is that right, Friendship 7? Yeah. Or one of the Mercury program capsules, I think, is in the Air and Space Museum. So you've seen it. You know, you've seen it. You've all seen it. If you've been there, you've seen it. And now you've seen it as a picture. Okay, so here's the spacecraft. This is a picture of it when it was, I don't believe it had been moved to Florida. I think this was the picture when it was still at the Applied Physics Lab. So Johns Hopkins Applied Physics Lab in Laurel, Maryland, they are the manufacturers of it. They're going to operate it. NASA Goddard, as I says, they operate, they are the managers of the Living with a Star program. There are 4 instrument suites on the spacecraft, okay? It's primarily measuring things locally. There is a camera, but this camera is not going to look at the sun. Again, for obvious reasons, okay? We're getting really close to it. Looking at the sun would be very difficult to do. So it's looking at the corona. It's looking off to the side, okay? These instruments, these 3 instruments are in situ. So we're measuring locally things. We're measuring things like the magnetic field. Okay, because we want to understand, because the magnetic field basically is everything in the corona. The magnetic field is very, very strong. That's where the energy is. Okay, so if you can understand the magnetic field, you can understand things like the solar wind and how energy is, how the solar wind's heated and the structures and so on. So we need to understand the magnetic field. So there's a magnetometer on board, and it'll also do waves and radio waves. And then there's sweep. Sweep is the solar wind detector. So that's actually going to measure the solar wind. Okay. And these are the PIs, Justin Casper from Harvard Smithsonian and the University of Michigan, where he's actually located now. Stuart Bales at UC Berkeley. Then there is ISIS, excuse me, slip of the tongue. It was initially called ISIS when we proposed the spacecraft back in 2010, but along came something in between, and we realized we should change the name. Okay, so it's pronounced ISIS, and there's a solar symbol there. Okay. EPI is energetic particle instrument. The PI for this is David McComas. Interestingly enough, it is an energetic particle detector, so it measures the high energy radiation. That's snow, but it also is going to measure these particles locally with detectors. This stands for, well, I'll talk about this mission in just a second. And then there are this instrument in a second. And then there's WHISPER. WHISPER is the wide field imaging thing. It's going to look off to the side and look at the corona. And we're hoping that there's going to be periods when we see stuff in the corona, structures coming off, and that we fly right through them, that we could then measure locally. Because we're going to be flying very fast by the sun. Okay? And then we also have this sort of level of a instrument on the team called the mission astronomer, if you will. Marco Velli is at UCLA. There's a large part of this is to try to understand these observations. There's a lot of theory and modeling that has to be done, and he's sort of the lead of all of that. And he is also the lead of the theory and modeling team, which is, encompasses all of these. I'm a member of that as well. And then I'm also, as is another member that's I'll talk about in a second, that is also, so a couple of the Arizona people are involved in this spacecraft as well. Here's the thermal protection system. So it's basically a big carbon composite thing sitting out in front of the spacecraft. It's going to get extremely hot, 1400 degrees Celsius at its closest approach. But the instruments will be room temperature. Think about that. Over the distance of about Friendship 7, you go from 1400 degrees on one side to room temperature on the other side. Okay? And that's because, well, in space there's no atmosphere. Well, there is, but we're not getting so close that you feel the atmosphere so much. Okay? It's still very tenuous. It's kind of one of these interesting concepts. The kinetic temperature of the region we're going to be experiencing is going to be very hot, 100,000 to 1,000,000 degrees Kelvin. Okay, that's the kinetic temperature. But the sort of thermodynamic definition of temperature that you equilibrate with your surroundings, the temperature you feel, will not be that because there's not enough of the particles hitting you. Okay, so you can't really equilibrate with the surroundings. So they're going to be room temperature, and that's because there's no atmosphere, so to speak, and it's here on Earth. You go into the shade. Okay, maybe in Tucson it's a little better than places where it's very humid, but you go into the shade here in Tucson, it's a little bit cooler, but it's not going to be as cool as if you had no atmosphere at all. Okay, going on, like if you're an astronaut on the moon and you're in the sun, it's probably pretty hot. You go into the shade, it's like freezing cold. Okay, so so that's the thermal protection system which sits out front. The spacecraft, as I said, is going to be moving very fast. So you might wonder, we're hiding behind this big heat shield. Why? How can we measure anything at all? Well, we're doing it by virtue of its motion as it goes around. So there's the anti-ram is the backside. So imagine this thing sweeping around. The back side of it, that's this side, has a couple of detectors. It's okay. So these are the radio antennas. This is the boom where the magnetometer's on. There's a couple of solar panels, and then sweep. A couple of solar wind instruments are actually part of sweep, and maybe during the question and answer period, our faculty member involved with sweep can tell us why on earth would you possibly sit something out on top of the heat shield to look at the look at the sun. But and then there's another component to sweep on the backside. Let's just call it the backside. And then on the front side, that's going to be collecting things coming in. Aberration, when you're walking in the rain, you hold an umbrella above you, you still get rain in the face. You have to tilt the umbrella a little bit. It's that same sort of effect. This thing is moving so fast. So most of these instruments are going to be collecting things on the RAM facing side. Okay, I mentioned the University of Arizona. This is our group. Some pictures are just a portion of our group. I have a long list of names. I want to point out a couple of people. So that's me. Christopher Klein, who's right down here in the front. He is a member of the Parker Solar Probe Sweep Team. I'm a member of the ESIS Energetic Particle Team as a co-I. I would also like to point out Randy Giacalone. He's a very noted cosmic ray physicist, a member of the United States American National Academy of Sciences, a very renowned cosmic ray physicist, Joseph Coda, Walt Harris, Federico Fraschetti. This is part of our group, and we have a number of other people that I couldn't grab pictures for and fit them on the slide. We study cosmic ray transport in the solar system, the solar wind, interplanetary magnetic fields, the heliosphere, fundamental physics of space plasmas, which is a very rich and diverse area of physics. It's classical physics. In some sense, Isaac Newton and Maxwell did it all for us a long time ago. But I found that's not true. Okay? Physics is beautiful, enriching, and subtle. Even classical physics has lots of unsolved problems. And then a lot of our work extends to astrophysics, and so it's got broad astrophysical applications. Mostly we're theorists here at the U of A. I do a lot of numerical simulations, sophisticated large-scale simulations. I did that again. And that's basically been our forte for many years. Randy Giacalone is a noted theorist. Okay, as I still have a few more slides, but I want to have some questions. I want to talk about the naming of the mission to the Parker Solar Probe. I just want to go through this very quickly. So we renamed the mission last October 2017, named after Gene Parker, who I'll talk about in just a second. Parker's the one that developed the theory for the solar wind. He's too a theorist. He was Randy Giacalone's postdoc advisor. Okay, and I came here to work with Randy Giacalone. So in some sense, I am a grandchild of Gene Parker, right? This is Thomas Zurbuchen. He is the current director of the the Space Mission Directorate at NASA. Very high up in the NASA chain, about as high as you can go. This is Nikki Fox at the far right. She's the project scientist, good friend of mine. And this is Marcia Neugebauer. I don't know, is Marcia here? I was really hoping Marcia would be here, but I haven't seen her. Marcia Neugebauer is the one that saved Gene Parker's job. Okay, Gene Parker was a theorist, predicted the solar wind, and it was criticized at first. People didn't like it. It was a theory, and that theory sat around from 1958 to like 1962, or maybe 64. I might have the year wrong. When she was the PI of an instrument on Mariner 2 that was going to Venus, and measured the solar wind for the first time, just as Gene predicted. Okay. Marcia's accomplishments are enormous. She's had a very long career. She spent most of her career at the Jet Propulsion Laboratory. She moved to Tucson about 10 years ago. She's living at the Arizona Senior Academy Academy Village out east. This is the first NASA mission named after a living person. Here's Gene. I had to throw an equation in here. I am a theorist. this is his famous equation for the solar wind speed. I derived this in my graduate level space physics class. This is the famous paper, 1958, received in January. I should point out that the referees for this paper, both of them unanimously, or both of them categorically said rejected this paper, should not be published. Okay? The editor was Chandrasekhar, famous Nobel Prize physicist, who was just down the hall and said, told Gene, you'll be amused by these referees' reports. Okay? And Gene was trying to explain to him how wrong they were, and Chandrasekhar says, you don't need to say anything, I'm going to publish it anyways. Okay? And it's a good thing he did, because Chandrasekhar is a very careful guy who went through it all himself too and knew. So, anyways, that's Gene, Thomas, Tom Cremegis, Thomas Zerbuka, Nikki Fox right here at APL. Okay, and then there's launch. I'm going to go to this launch. I'm very excited about it. August 4th, my first ever launch. The launch window starts August 4th, goes to August 19th. Okay, so we have 2 weeks. It's largely determined by where Venus is, because we're using gravity assists from Venus to get to the sun. And if we miss this if we don't launch, if there's a hurricane, let's pray for no hurricanes. It's being launched out of Kennedy Space Flight Center in Florida, Cocoa Beach. I'm going to be there for a science meeting the week before, and then I'm going to stay a couple extra days. And I'm really hoping it launches on August 4th or August 5th. It's being launched with a Delta IV Heavy. That's what this is. This little video is. Yeah, it's got we're basically going to Venus at first, and then eventually getting to the sun. I was reading the itinerary for this. I didn't realize until I read very carefully the details about the launch. I have to check in at 1:30 in the morning. Okay, I have to check in. Takes me to the visitor center at Kennedy Space Flight Center. And then a bus takes us to the launch site, and the launch is between 4 and 5 in the morning. So I'm looking really forward to it. I kind of view this as a very important thing for me to do. And this is what's going to happen. It doesn't look like it's 4 in the morning for that launch, though. That looks like more like 9 or 10. That's a manageable time. But just imagine, solar probe is this little tiny thing at the very tip of that. So yeah, if we don't launch during this period, we have to, my understanding, and I know I'm being recorded, so I guess it's for posterity. All the world can hear my quotes here, but don't quote me. I think the next launch window isn't until February, so it's really important that we launch during those. Because it depends on where Venus is. Anyways, okay, so that's the launch, and let me just try to skip through the last couple slides really quickly. I haven't even talked. So there's the orbit. We have many of these passes by Venus. Let me show. Actually, this one is, I know it's a graph. It looks a little complicated, but each one of these are Venus passes. This is the distance to the sun. Okay, 0 being, I guess, the center of the sun, or maybe it's above the. Well, I don't know. I don't know if 0 is the center of the sun, or I don't think it matters too much. But anyways, here's 1 AU. We go down, and you can see the orbital period changes to about 88 days. Every time we pass Venus, we change the orbital period and the orbital semi-major axis a little bit. We just get closer and closer, progressively closer. It's a long mission. We don't, even though it looks like we're going to the sun, it's 1 AU away. How hard can that be? We're not going to get there. Well, we're going to make a very close pass in November of this year. Closer than any other spacecraft has ever been. But we're not getting to as close as we want inside of 10 solar radii until 2025. Okay? So it's a long mission. Okay, another technical graph, but I just wanted to point out the relationship between distance and speed. The speed is the green curve. Distance is this curve. So early on, the changes are fairly big, but nothing major. But by that last one, when we're getting really close, the speed approaches 200 kilometers per second. That's 420,000 miles per hour. Okay, that's how fast we're going by the sun in 2025, and we're getting very close. So this is Kepler's laws. Okay, if anybody knows Kepler's laws, okay, Kepler's laws tell you that the closer, your speed increases at a highly eccentric orbit at perihelion. Okay, and then I just wanted to show this because I think it's kind of cool. There are periods when we're actually, if you're on the sun rotates. Okay, rotates, the equator rotates at about 26 days, 27 days. The poles rotate a little slower. But if you're at the sun looking up at the Earth's orbital speed is like 20 kilometers per second or something like that. So the Earth moves one direction if you're on the surface of the sun. But our orbital, it's hard to get a heliostationary orbit. You'd have to get really close to the sun for that. But it's going to be going so fast that there are periods that when viewed from the sun, we're going to be co-rotating with the sun, okay? Hovering over a single point on the sun for a couple of days. I wish I could have stopped it there. But you saw that looping back, that's called the retrograde motion. And at the end of those two orbits, end of those two spots there, that's the co-rotation period. And those are about a day or two. So for a day or two, we're going to hover over one spot of the sun. And that's really important to study the solar wind. I'm going to skip past, but anyways. Okay, just really quickly, I want to go through these science objectives. So one of them is to study what heats the solar wind and the solar corona. So we're going to answer questions like how is the magnetic energy converted into thermal energy for the ions and the electrons. That's basically what we're measuring. The solar wind is composed almost totally of protons and electrons. There are some other particles as well, but protons and electrons. The other particles are important as diagnostic tools. And then how does this change with distance? And our distance is changing dramatically over short periods of time. Also interested in the structure. How does the solar wind change? So this is a coronagraph image, and you can see there's a lot of structure there. And so we're hoping with WHISPER, which is the imager, we'll see something, and then we actually fly through it and measure things locally. Okay? So we're going to be able to determine structures and how magnetic fields connect back to the sun and open up. And then there's this, the energetic particles, which is my instrument, or that I'm a co-investigator on this instrument. What is the mechanism that accelerates these particles? We do see acceleration at 1 AU, but we really need to get close to the sun to see the acceleration near the sun. And there's actually a lot of debate among theorists and the scientific community about what we see at 1 AU. What's happened back near the sun, because a lot of the wiggle room is that we just don't know what's going on near the sun. So we're going to get close to the sun to see some of this. Because these particles here that you see the background, the actual corona that produced these particles, but the particles at 1 AU are coming out very, kind of like the speed of light. So they come out in like 10 minutes, 20 minutes, 30 minutes, a little bit slower than the speed of light. Whereas the CME is still back near the sun. So the acceleration happened at the sun. So we want to get close to it to see exactly what's going on close. And then this is another final movie, just very quickly, and then I'm going to finish with a couple of other things. This is basically the spacecraft. This one could have been attached to the launch movie, showing what's going to happen. The separating, flying above Earth for a little bit. I guess it's got to do that. And now it starts to make its journey. There's that great heat shield to keep everything nice and cool. These are the solar panels that came off. And then that's the magnetic boom. You got to keep the magnetometer as far away from the spacecraft as you can. And there's the radio antennas. And then it orbits gets close to the sun. It starts by Venus. It does a Venus transit. No Venus science, unfortunately. Our passes by Venus are prime times for downlink back to the Earth. And it does have a very sophisticated computer on board, so it will store most of the data, and then we send it back in chunks at prime time, where it's not a continual sending back. Okay, we store it, then we send it, and then we analyze. Okay, and the Venus encounters are prime; those happen during prime downlink periods. And by the way, yeah, the computer is considerably more sophisticated than that on Voyager, which is basically nothing. Voyager didn't have any capability to store stuff, right? And then here's the orbit that I showed, and then here it is getting really, really close to the sun. I'm looking forward to that. That's exciting stuff. I think it's exciting to get very near the sun. Let's just hope. Okay, I hope there's a massive coronal mass ejection that happens right at that time. I don't think the engineers or the other instrument PIs want that, but I do. Maybe at the end of the mission or something. Okay, social media I got to put down there. Hopefully everybody had a chance to get their name sent to the sun. Did anybody Was anybody aware of this? I hope some people sent their name to the sun. There was a website you could go on. You attach your name to a chip. And here's the chip right here. And that chip with a plaque that talks about Parker's quote, let's see what lies ahead, is being attached to the spacecraft at APL and is being boarded on this Delta IV Heavy pretty soon and going to the sun. If you're into the social media, here's all the different handles, Twitter handles, Facebook page. Solar Girl 2018, that's Nikki Fox. She's the project scientist. And I think she probably also does the Parker Sohn probe. And I just want to finish. I have one last slide, nothing to talk about. I just want to end it, and then I'll take questions. But I just love these pictures. So, okay. So, yeah. Anyways, that's all I have. I'll be happy to take questions. So, yeah.
We've got a couple of microphones. So, Bert?
I don't think I need a microphone.
Yeah, you do. We're recording, so.
And I may rely on the other investigator in the audience here to answer some questions as well, or my son, who's also in the audience.
Okay, I'm grateful I passed my electives in 86 and 87. I came here for entertainment. However, I didn't expect to have a question. My Cracker Jack box understanding of magnetic fields is it takes an iron core as Earth. So what generates a magnetic field in the sun?
Excellent question. Yeah, that's a very good question. Okay, so on Earth, it does take an iron core, but there's another, and the reason why iron, okay, is because it's a very good conductor of electricity, okay? But there's another component on Earth to not just being iron, but also the fact that it's in a liquid state, that it's molten. And the reason why that's important is because we can get a differential motion of the fluid so that some parts of that are spinning differently than other parts. If you had something solid like a cue ball and you were spinning it, all parts of that cue ball spin at the same rate. But when it's liquid, you can have what's called differential rotation. Okay? And in the center of the Earth, we have some parts of that. We don't have a probe in the center of the Earth. But if we did, we're quite confident that some parts of that liquid part of the core would be spinning at a different rate than other parts of the core. And the magnetic fields, for a case for high electrical conductivity, or electrically conducting like iron is, the magnetic field is actually forced to do whatever that fluid does. So you could imagine a rotating, something rotating differentially that's carrying magnetic field with. That magnetic field gets twisted up and bound up like a rubber band, okay? And it turns out that that's what's essential in the generation. This is what's called the dynamo. And that's what's essential for the Earth to generate the magnetic field, okay? For the sun, a plasma, okay, which the sun is. The sun is basically a big ball of plasma. That's protons and electrons. It's basically a gas where you get rid of the electrons and protons aren't bound to each other. That is extremely electrically conducting, much more so than iron. And it's also a big ball. Actually, I was going to say one more thing. The sun is not entirely plasma. The photosphere, actually what we see is actually mostly neutral gas. But the rest of the sun, other than that little tiny thin layer of the sun, is a plasma. But the sun also, being a big ball, differentially rotates. So we know the equator rotates more rapidly than the poles. So we have the dynamo action on the sun. That's the same thing. But that's an excellent question because if you take just a bar magnet, you magnetize it, a bar magnet, and then you heat it up, the magnetic field goes away. Okay, something called the Curie effect, the Curie temperature. Once you get a certain temperature, the magnetic field goes away. That's because that magnetic field is caused by the actual orientation of the atoms that make up that bar magnet. But in this case, it's a dynamo. You're actually relying on the large-scale motions of the inside of the sun. But that's an excellent question.
Will the heat shield reflect light from the sun, and if so, can the instruments detect it?
That heat shield is it will almost certainly bounce something off back towards the sun. I don't think any of it could be detected because the instruments are all kind of like hiding behind it, and all of that bouncing will be off the other way. So, but there is a possibility for some of the radiation that's produced on that heat shield that could potentially be measured behind it. Let's hope not, because that's what we call an instrumental effect, and we're trying to measure real physical effects and not instrumental effects. The heat shield itself, it's a carbon composite. It's meant to basically, absorb the energy, try to reflect as much as possible. But hopefully we can't measure anything produced by the heat shield. The heat shield is really literally designed to keep the instrument safe. So let's hope not. But that's a good question, because if so, then we're not measuring something real. We're measuring something bouncing off. Yeah.
Now, because you're going so close to the sun, do you have to use general relativity to calculate the orbits, and do you have to allow for time dilation and gravitational redshift?
Okay, time dilation would require speeds approaching the speed of light. So it's not
Gravitational time dilation.
okay.
General relativity.
Yeah, well, okay, first of all, that's a good question. My feeling is that the orbital mechanics can probably be dealt with mostly with classical mechanics, but probably general relativity comes in. I mean, certainly the precession of Mercury's orbit is a very well-known thing. The precession of Mercury's orbit was not very well understood until Einstein came along, and probably that kind of effect also has to be included. Chris, I don't know, do you know the answer to that question?
Yeah, so the engineers who've done the orbit planning have taken into account the general relativity effects and have made sure that the 24, 26 different orbits that have been planned out all have been calculated, including those effects beyond
Interesting, yeah.
classical mechanics.
Yeah. Yeah. I don't know. I'm not the one with the microphones.
What happens to the probe after 2025?
It will continue, and hopefully NASA will continue to fund it. It will continue to measure things. It will go, so I don't think there's any plans to smash it into the sun or anything like that. I think it's going to fall in line with the sort of normal way NASA operates, that it goes into prime phase in 2025 to maybe 2026. And then after that, it goes into something called senior review. We have a bunch of other spacecraft up there right now, close to Earth, that also look at the sun or interstellar space or what have you. And you have to justify their existence after that. They become big floating laboratories and telescopes that measure things that are important, presumably, but you have to justify that, because this is being funded by you guys, by taxpayer dollars. And if it's no longer serving a purpose after its prime phase, then it'll just be, to be discovered in the future.
And fuel runs out and instruments fail.
Yeah, but that's going to take some time. Yeah, that takes some time for that to happen. I mean, look at Voyager. Voyager was launched in 1977. Here we are. It's 150 AU out there. It's still going. Yeah. But no, others like Ulysses was not. Ulysses was another spacecraft. Didn't last as long as Voyager. I don't know who's got.
I've got a question. The orbit itself, it's you've been in orbit now for a while. You're all nice. It's not really like a classic planet going around the sun. It keeps zipping back and forth, back to Venus, back to the sun, so it's kind of doing this back and forth.
Yes.
Okay, that's
highly eccentric orbit. That's right. That's the way to get close. Getting to a circular orbit about the sun at a distance of 10 solar radii, moving, whatever I said, 400,000 miles per hour.
Yeah.
That would be very hard to do.
Okay. Yeah.
It's hard to do that. Even going to Mars, for example. So you start with an orbit around. You're in a close to circular orbit with the Earth. You get launched, and then you actually do something called a Hohmann transfer orbit, where you go from this to an elliptical orbit. You're actually in an elliptical orbit for a while till you get out to, say, Mars, if that's where you're going, and then you've got to do an energy change there in a way to get you to stop. Okay, and then otherwise you just come back. And then to achieve the circular orbit around Mars actually requires, this orbital mechanics is all fun stuff.
No, it's weird stuff.
Yeah.
But
yeah.
the fact that you're actually close to the sun and farther away than back, it actually can help with your science too, because you're getting data at different points.
That's true, and data will be collected during most of that, but there's also downlink periods, and so the prime phase of the data that we're going to be looking at is mostly when we're close, but absolutely there will be some radial, dependence to our data. And we also have other spacecraft, by the way. This is not operating in a vacuum. We do have other spacecraft that will be up measuring things, and so there's coordinated studies being done as well.
I was just curious about coronal mass ejections.
Yeah, I am too.
So I figured I would seek a like-minded person and ask my question.
Yeah.
Do they travel radially outwards from the sun? Do they have the velocity of the surface of the sun? What kind of a path?
Okay, so they expand out. They expand out radially. They're quite a bit faster than the solar wind. Okay, they're essentially probably just to sort of set a picture. So the coronal mass ejection strictly is something that when you look at a coronagraph and you see this big sort of arching looking thing, that's what a coronal mass ejection is. We do see their counterparts at 1 AU. They're called interplanetary coronal mass ejections, and we can see them when they come by, and we know a great deal about it. They're basically a large magnetic, just imagine like a torus, if you will, wrapped magnetic fields that just keep extending out as we go out. And even at 1 AU, we think it still connects back to the sun when that happens. But it is expanding out radially, and they have a variety of speeds ranging from a few hundred kilometers per second, about the solar wind speed, to 3,000 kilometers per second. So they can go out considerably faster from the sun. But they're basically, okay, so if you go out and look at some of those images out there, you might see something called a filament on a picture of the solar chromosphere. You see these snake-like looking things. That's a cold, dark material that's being supported by little magnetic fields underneath. That turns out to go unstable at some point, and the whole thing starts to rise. But as it's rising, the magnetic field is entrained inside of it, and then at some point it explosively erupts off, causing this big arching structure that shoots off at several thousand kilometers per second in some cases. But yeah, we don't understand. So you're kind of getting at what is the origin of coronal mass ejections. That's one of the fundamental questions. But that's what they are. What they are is big chunks of solar mass contained by these toroidal-like magnetic fields. Possibly still connected to the surface. In some cases are. Sometimes we look for these with high-energy electrons tell us the structure of the magnetic field. And sometimes you see that only one end is connected, and both ends is often connected, yes. But how far out does that go before it becomes totally disconnected is not well known.
We'll take a couple more questions.
How did Carrington figure out that there was a connection there?
I think he made the connection through the aurora primarily. First of all, he said, do you want to answer that, Chris? Yeah.
So Carrington actually was looking in white light at the sun, and the sunspots are actually much darker. The magnetic fields are much stronger there, and so he was able to actually, by eye, he just happened to be looking at the sun indirectly, actually it has a hand drawing of this sunspot that then a few days later was associated with these incredibly strong aurora that were observed on Earth and this Carrington event that came through. So,
yeah. I think he also saw white light. Okay, you can see flares in white light occasionally, what's called a white light flare. You can see features around where there's a sunspot, but you can also see the white light thing. I think he also was the first to note that, I believe, as well.
Yes.
Yeah. So this was a special one. I mean, we've been seeing sunspots for some time, but this was like a really big one, and you see these white, what are called two-ribbon flare. It's called a two-ribbon flare if you want to go Google it later. But he could see that in white light, and that's very rare to see these white light. Yeah.
Yeah, maybe I missed this, but could you say what the distance from the sun when you reach the final desired orbit in 2025 is, the aphelion, the perihelion, and what the orbital period is?
Yeah, I went through that too quickly, didn't I? It was this graph, I think it was. So the orbital period is at the far right, and this little yellow box up at the top. So orbital period is 88 days. And it's going to get, okay, so AU, it's going to get just like 10 solar radii, about 10 solar radii. Okay, I think that's pretty close. I mean, it'd be nice to get to like 1.01 solar radii, but I think that would be a very short trip. You know?
Okay. Let's thank Joe again.
Thank you all.
And you can check out the display of the heliopause that's out there with the water, and you can check out the movies next door. Thanks for coming.